Okay. Moses here now. Right now, yes, I will put it on the YouTube. Yes. All right. Who's Jojo Tanks? Can we disprove the other answers? Can you disprove them? Oh, if you want to, yeah. Okay. All right. It's twice the bond energy of the CO bond. Right. It's saying that. All right. You want me to disprove that one? Okay. Right now, well, the CO bond, it's not. It's not. Why would it be twice the energy of the CO bond? Carbon dioxide is a triple bond anyway, isn't it? So it's got nothing to do with that. I don't know. That's absolute nonsense. That one. It's the energy released when 1 mole of carbon dioxide is formed from carbon at the temperature of combustion. Well, that's not standard conditions, then, is it? So C is wrong. It's the same for carbon dioxide produced from graphite and from diamond. That's not right either. Okay, I'll show you an interesting thing actually. Okay, which I did recently with the lower middle six. Okay, there is an energy diagram, and on the left we have energy, and on the right we have some reaction coordinate. Reaction coordinates. Okay, and imagine this reaction: carbon as graphite goes to carbon as diamond. Okay, and this I believe is 3 + 3 kilojoules per mole. Okay, there you go. So graphite, carbon as graphite turning to carbon as diamond is a change of 3. So let's draw this on this thing here. Well, this means this is carbon graphite. God, everyone wants to come in today. I don't know. There's carbon as graphite, and diamond is a little bit higher, isn't it? I think everything's going wrong. So diamond is higher, and the difference here is 3 kilojoules per mole. Okay, so let's see what we can guess from that. All right, if I burn 1 mole of graphite and I burn 1 mole of diamond, which one will I get more energy out of if I burn 1 mole of graphite or 1 mole of diamond, according to this diagram? Anyone want to guess? Anyone can guess. No one. All right. Diamond. Yeah, you will get more diamond. Now let me draw a line here. Yeah, no, Jojo takes. All right, there is carbon dioxide. Carbon dioxide is carbon dioxide. There's nothing special about carbon dioxide. But if you burn graphite, you'll get this much energy out. But if you burn diamond out, you'll actually get more energy out. Does that make sense? Yes, Jojo. always change your answer to the other one. Okay, so believe it or not, from this simple expression up here, I can tell you that if I burn 1 mole of graphite or 1 mole of diamond, I'll actually get more energy from diamonds. Now, using this as well, which one has the strongest diamond or graphite? Which has the strongest C bonds? Which one, graphite or diamond, has the strongest CC bonds? Anyone at all? Diamond. Everyone says diamond, but you're all wrong. Okay. Now look, and you should use this diagram. That's why these diagrams are good. If we break a CC bond, what we're going to get? We're going to get carbon gas. Yeah? And there's carbon gas. How much is it going to? I'm going to use that energy to break graphite. But believe it or not, breaking diamond into its atoms is cheaper. Can you see that? Anyone? Do you understand that? So believe it or not, vaporizing 1 mole of graphite is more expensive. It costs more than 1 mole of diamonds. So if I vaporize 1 mole of graphite and I vaporize 1 mole of diamond, what bonds am I breaking? I'm obviously breaking carbon-carbon bonds, aren't I? Yes? So which one requires more? Well, the one that requires the more energy has the stronger carbon-carbon bonds. Does that make sense? Anyone? Argue if you want. Yeah, that's it. That's why these diagrams are so useful. All right. Now, if you think of diamond, diamond has single covalent bonds. Yeah, no, it is insane, isn't it? It's crazy. This is diamond, and you're breaking a carbon-carbon bond. But if you look at graphite, what you're breaking is this. You're breaking these bonds here. But don't forget this is like 1.5 bonds because the p orbital delocalizes. So in diamond you're breaking a CC. In graphite you're actually breaking kind of 1.5 bonds, and that is stronger. It's crazy, isn't it? But the point I want to make is not to try and impress you with the properties of graphite and diamond, is to see and understand how useful these diagrams are. Because if you get good at using these diagrams, you can answer so many questions. You really can. But you've got to get good at these diagrams. All right. Anyway, let's go back to you. Who's this? Jonathan's here. Jonathan. Well, yeah, well done. Jonathan's here. Right. So are we good with that? I'm going to move on to the next question now. So the question there is equal that the A is the answer there. All right. Now use data booklet relevant question. Hydrazine is used as a fuel in the Messerschmitt, and for that it has the following formula. What is the energy of atomization of 1 mole of gaseous hydrazine? Now, obviously, I don't know if you can see. I don't think you can see it anymore. But I'm looking for my data booklet because I'll have to open it on the other screen. What I want is another screen. I want 3 screens. All right, because that would be nice, I think. It's opened it, but it hasn't opened it where you can see it. All right, so there you go. You should be able to see that again. All right, here we go. There we go. All right, data booklet is open. I should have really opened this before, shouldn't I? Okay. Okay, so what bonds do I need? I need the NH bonds. And according to my data booklet, the NH bonds, this one has a bond energy of 390. And a nitrogen single bond nitrogen is 160, apparently. So this one is 160. Okay, so that's all I need. Let me turn the data booklet down for a bit. All right, so if I'm going to atomize this, well, basically, if I have hydrazine on the left, N2H4, I'm going to get NN, H, 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 aren't I? I'm going to break all of those bonds. And therefore, what am I breaking? I'm breaking 4 390s, and I'm breaking 160. Now, I do have a calculator, but I don't know if it works anymore. All right, 390 times 4 is equal to that, plus 160. 1720. So there you go. That's the answer. Are there any questions about how I did that, or do you understand that, guys? Don't be quiet. If you don't understand something, you got to say, "Look, I don't know how you did that," because you've got to start picking at those horrible, irritating things. You've got to get an A in this, seriously. And you can all do it, but you've got. Oh, well done, Moses. Thank you. All right. Now the next one. Here we are. Now this one. These multiple choices is tricky, I tell you. All right, gaseous phosphorus pentachloride can be decomposed into gaseous trichloride and chloride. The table gives that. What's the enthalpy change of the decomposition? Okay, so basically, this is how I would do this. I don't know how you guys would do it, but maybe it's the same way. I would say PCl5. So there's PCl5. I don't think I do this in an exam, but if I'm revising or if I'm learning the subject, I draw lots of pictures, and I get that. Okay, so basically, what am I doing? I'm breaking. What am I breaking? I'm breaking 2 of these, so that's going to cost me plus 330. That breaks 1 because that's the bond energy for a PCl, and that's times 2, so that's going to be 660. All right, plus, because it's endothermic. And I get out a new ClCl bond. My new ClCl bond is minus 240. So I add 660 to minus 240, and that's going to give me 4 something or other, plus 420. So there you go. That's the answer to that one. Any questions there? Any one at all? I don't mind. You don't have to. Oh, this is the one I was just looking at. All right. Are we good there? Are we good? Anyone want to say anything? We're good. Oh, whoopsie daisy. Okay, you don't get it. Why don't you get it, Basadi? What's wrong? Turn the microphone on if you don't get it. Thanks, Jonathan. Go on then, Basadi. What's wrong? Talk in your posh voice. Basadi, anytime you're ready, dear. What don't you get, darling? Anytime you're ready. What? You said you don't get it, and then you've said what? Basadi, what's wrong? Turn on the microphone, dear.
I'm telling
Oh,
you.
Jesus, dear. You don't have to shout. Went straight in my ear, that. Bloody hell. Go on then. What is it?
I don't understand the whole thing. Like,
Really?
this start from the beginning.
On this question?
Yes.
Oh, okay. All right. We'll have to wait for Basadi. Basadi, this isn't hard. All right, but I mustn't say that. Okay, that's mean, isn't it? All right, so let me get rid of all this for Basadi. All right, let's pretend we don't know the answer. All right. Mm-hmm. Bloody hell, this is taking forever, isn't it? Oh, we're recording. I shouldn't say bloody hell. Oh dear. Right, here we go. All right. Now, first of all, PCL5. Now, Bazali, I'm looking at the screens, especially for your comments. So we have PCL. Would you agree that this is PCL5? Just a Y for yes. Do you agree with that? Yes? Y for yes? Anytime you're ready, dear. I'll continue. Well done. And according to the equation, or according to the question, we get PCL3. So we get that. And we get that. Okay? So on the left, I have to break bonds. And on the right, I must form bonds. Okay, breaking bonds is, as we all know, endothermic. So that means I've got to put energy in to break them. Forming bonds is exothermic, so I get energy out to when I form bonds. So which ones am I breaking? Well, as you can see, I'm breaking two. I'm breaking one of those and one of those. Why am I only breaking two? Because I end up with, I've got PCl3. I could break all five if you want and form three, but that's the same as just breaking two, isn't it? So now I'm going to say I break one. Breaking one of those is going to cost me 330. And breaking the other one is going to cost 330. Oops. So to break those two bonds, it cost me, I have to put 660 in, so that's plus. Now, what is formed? Chlorine is formed. Chlorine apparently has a bond energy of 240. So when a chlorine atom joins with another chlorine atom, 240 is given out because it's bond formation. So the overall enthalpy change of the reaction, here we go, overall enthalpy change is delta H is equal to how much you put in the endothermic bond breaking part plus the exothermic bond forming part. The endothermic part is 660. The exothermic part is minus 240. So we get 420. And that's the answer there. Is that reasonably okay now? Okay, well done. Okay, now the next one. This is the one I was talking about, believe it or not. There we are. Let me make it a bit big. I'm not too big. There we are. All right. This is the one I was talking about. I forgot about this. But this is, students find this a really hard question. It's not. Okay, the conversion of graphite into diamond is endothermic. There. The statements are correct. The enthalpy change of atomization of diamond is smaller than graphite. That is true, isn't it? That's true because diamond is higher than graphite by 3. This is graph and this is diamond. So if you're going to atomize them, the atomization energy of diamond is going to be smaller. I hope you get that from the diagram we drew earlier. The bond energy of the CC bonds in graphite is greater than diamond. Well, that must be true because to create atoms of carbon, it costs me more. If it costs me more, the bonds between the atoms must be stronger. The enthalpy change of combustion of diamond is greater than that of graphite. So that's true. And this is true because when we combust graphite and when we combust diamond, they go to the same thing. But because diamond is higher up than graphite, obviously turning diamond into carbon dioxide is going to give out more energy. Anyone want to argue with that? If you don't, I'll go to the next question. Okay, are we good? Oh, this next one looks awful. Okay, this next one. Why does it do that? It puts it weird size. All right, there we go. All right, let's make it there. Okay, this one. Oh, what's going on? All right, so are we all good there? But again, you've got. Can I explain again? Okay, which one? That one. That one, Moses. Okay, let's put that one back down here then. Okay, now this is a good question. You know, you're not going to get any of these questions again. These 1, 2, 3 questions. Yes, they're not on the syllabus anymore, but it's good for your chemistry. Okay, so look, this is the information we're given. The conversion of graphite into diamond is endothermic. Okay, so what I decided to do is to do this graphically. This is what I would do. Okay, so if I convert graphite to diamond, there's graphite, carbon, there's graphite, and there's carbon, there's diamonds. Oh, that's ugly, isn't it? Now, if I want to, and that's basically it, and the difference there is 3 plus 3. So the first statement says the enthalpy change of atomization of diamond is smaller than that of graphite. Now, to atomize graphite, I'm going to get carbon gas. If I atomize diamond, I'll get carbon gas as well. But can you see that if I atomize graphite, it's actually going to cost me 3 more than atomizing 1 mole of diamond? Does that make sense, Moses, now? Because graphite to diamond, okay, that's cool. All right, now, from argument number 1, argument number 2 must follow. If the energy to atomize them is greater, it must mean the bond energy of the CC bonds is stronger in graphite. You're right. So in diamond, if I break CCs and I get carbon, but if I do it in graphite, it's going to cost me a little bit more. It's going to cost me 3 kilojoules per mole more. Okay, that means these bonds in graphite, the carbon-carbon bonds in graphite, must be stronger. They must be stronger because it's costing me more energy to break them up. Does that make sense? Are we good there? Excellent. All right, and the last thing is, if I burn graphite and burn diamonds, believe it or not, you can burn diamonds. Who's going to do that? But you can do it, and you get carbon dioxide. So if you burn graphite, I'll get carbon dioxide. If I burn diamond, I get carbon dioxide. But can you see that diamond has more energy in it than graphite does? All right. So I'll actually get more carbon dioxide. I'll get more energy out if I burn diamonds than carbon dioxide. Does that make sense, Moses? Are we good? Excellent stuff. So let's move on to the next one. All right. Yeah, these ones you just got to plow through, eh? They're hard, but that's what you got to do. Now, I don't want the answer to this one. This one looks horrible. Okay, so let me move that up and pull this down a bit. Okay, these ones are horrible, but let's see if we can dig it out. Why is CO2 at a lower energy level than graphite and diamond? Because when you burn graphite, dear, all right, let's see that one. Would you agree, Basadi, that if I burn some carbon, yeah, any old carbon, with oxygen, I'll get CO2? Would you agree with that? First of all, would you agree with that? Graphite is carbon, diamond is carbon. Yeah, I'm sure you would agree. Okay. Now, would you also agree that, yeah, energy is released when you're burning carbon dioxide? Yeah. So this, in other words, this reaction is going to be exothermic, isn't it? Because energy is going to be released. So if we did this on a diagram, carbon solids plus oxygen gas, the carbon dioxide would be lower, wouldn't it? Because it's an exothermic reaction. That's why we know that the carbon dioxide is lower than carbon in graphite and carbon in diamond. Is that okay? Is that good? Bizarrely, I'm looking at the screen. Well done. So you're good now. Are you all right? I'm going to go on to the next one unless you say otherwise, dear. All right, so let me pull that down. Whoopsie daisy. And push this up. These are good questions. You said yes. All right, yeah. Sorry. Right, at 600. Now, this one's going to be a hard one because I get confused by these. At 600 degrees, that's important. Oxides of nitrogen react with unburnt hydrocarbons in a catalytic converter in a car. The equation using methane as a representative of a hydrocarbon molecule will be as follows. So apparently, all right, nitrogen monoxide reacts with hydrocarbons. It gives us nitrogen and carbon dioxide and water. Okay, goes without saying. Which statement is likely to be true about the energy change in this reaction? Now, before we do anything, okay, do you think, all of you, this reaction is likely to be endothermic or exothermic? What do you think as a guess? Exo or endo? The overall. Bazali thinks endo because I think she guessed. So Bazali thinks endo. Anyone else? Now you've got to have a good feel for these things and look at those. Look at those. Look at those things. What do you know? All right. Now you could look this up in the data booklet, but you don't know a lot about this guy, do you? All right. You don't know an awful lot about these bonds, do you? So we have to break these bonds. Break these bonds. We have to break these somehow. But which bonds do we form? Well, we form this bond, and these bonds. Now, from your sort of everyday understanding of chemistry, what can you tell me about these bonds on the right? Are these very stable bonds or are they weak bonds? Are they stable or weak? Nitrogen, carbon dioxide bonds, and water bonds. OH bonds in water. Yeah, they're very, very stable. So if they're stable, when they are formed, will a lot of energy be given out or a little bit of energy be given out? What do you think? Anyone? Yeah, we get lots of energy. Let's draw an energy diagram for this. Okay, now, and I tell you, I know you think I'm going on about this a bit too much, but these energy diagrams, you've got to understand it in terms of these graphs. Okay, so what do we start with? Now, I can't quite remember. All right, we started off with NO. I think we had 4 of them. I can't remember. Who knows? And methane. We ended up with nitrogen. Oh, let me not colour these in yet. Okay. Now, first of all, what do we have to do with NO and CH4? We have to put energy in. Okay? Energy is going in to break these bonds. So I'm going to put energy in. Okay, this is the endothermic bond breaking. Okay, now once I put the energy in, I end up with nitrogen molecules. Sorry, nitrogen atoms. What's that guy doing there? I end up with nitrogen atoms, a couple of oxygens, and a carbon there, and hydrogens. Now, when these guys form, these form nitrogen, carbon dioxide, and water. Now, I know that nitrogen is crazy, 994, I think. These bonds in water are incredibly strong as well. They're strong. These are very strong. And carbon dioxide, carbon dioxide is a stable thing. So these are strong as well. That means when these guys form, they give a load of energy out. A load. So this reaction is very likely to be nitrogen, what was the other one? Carbon dioxide and water. This reaction is very likely to be exothermic. Does that make sense? Now, I know you don't know much about the N triple bond O and the bond energy of methane, but you do know that nitrogen, carbon dioxide, and water have very stable bonds. So in their forming, they give out a lot of energy. Does that make sense? All right. The more energy, all right, could you tell from the products? You can in this case because they're nitrogen, carbon dioxide, and water. They're very stable. Now, Let's see. Now, getting from this, a lot of you don't seem to have a grasp of what energetics means. It's not hard, guys. All right, let's have a look. If nitrogen, oh, let's do this again. This you've got to understand it from a simple place, I think. Nitrogen atoms. We've got nitrogen atoms there, and we've got a nitrogen molecule down here. Okay. One thing you know for sure that to break this requires lots of energy. You know that. You know that because we've said it a million times. Because it's a triple bond, whatever, whatever, whatever. But to break it, it takes a. But therefore, if the thing is made, it gives out lots. Gives out lots of energy. Does that make sense? So when nitrogen is formed, okay, when carbon dioxide is formed, and when water, oh, what the hell was that? And when water is formed, lots and lots of energy is given out. Why is that? Well, because these bonds are very strong. Okay, so nitrogen is a very strong bond. So when it is formed, lots of energy must be given out. Does that make sense? If you have a strong bond, it means lots of energy is given out when it is formed. It also means lots of energy must be used to break it. But they're two halves of the same coin. Okay? Does that make sense? Are we good? I hope so, Bizardi. I really do. Right, let's go back up to the question. So, looking at that question, I'm going to say it's going to be. Oh, that was Bizardi's question answer, wasn't it? I'm going to say it's exo because these are so strong. It's going to give out tons of energy, so it's likely to be exo. It's endothermic. Oh, rubbish. We don't like that one. Now it's going to be B, C, or D, isn't it? All right. Let's have a look at them in turn. B, it's exothermic as high temperature is required. Well, that doesn't mean anything. It just means that we need a high temperature, to break these bonds, but it doesn't tell you anything about these making those. So that doesn't tell us. It's exothermic as the triple bond is broken. Well, if this was very, very, very high, it wouldn't be exothermic. It would actually be endothermic. But it's not. It's exothermic. And that means the formation of the products gives out more energy than the breaking up of the reactants. I hope that makes sense. So that one looks rubbish to me as well. It is exothermic as the products have large enthalpy changes of formation. Now that is true, isn't it? Yes? Because apart from nitrogen, which doesn't have a large enthalpy of formation, because it is, oh, I guess we're forming it from the atoms, aren't we? So this one would be the answer. Because in forming nitrogen, carbon dioxide, and water, a lot of energy would be given out. So because of a lot of energy is given out, overall the reaction will be exothermic. I hope that makes sense. I really do. I'm moving on unless anyone wants to argue with that. But please argue. Okay, let's try this one. Maybe I should have actually got some paper 2 questions. All right. But the multiple choices need more help, I think, I'm afraid. The standard also, I think, let's have a look here. All right. Now you should use these lessons that we're doing now to make you realize that you don't understand stuff. I don't think you can learn. You can get an awful lot from these lessons, but it should point you in the right direction about what you need to learn. Okay. If you're not good at this subject, you've got to go back to basics. Eh? You can't just learn things on the fly. All right. I'm not very good at remembering stuff, but I'm quite good at the basics. All right. See if we can figure this one out. The standard enthalpy changes of formation of HCl. Oh gosh, what's happening there? And where are we? 65, 81, 90. Oh, it's all going nuts. All right, make that small. All right. The standard enthalpy changes of HCl and HI are 91, minus 91, and 26. Okay, and plus 26. All right, so there we go. All right, now what? Before we do anything else, let's interrogate what this means. Okay, which is I think you should do. You shouldn't just look for the right answers. You should interrogate what it means. That statement, what does that mean? Well, let's do the first one. HCl, all right, is made from hydrogen and chlorine, okay, and I get HCl, okay. I'm going to use half a mole of that and half a mole of that, and I get 1 mole of HCl, and that is exothermic 92 kilojoules per mole. Whoops, there's in minus. Okay, if I do the same with HI, apparently it's plus 26. So let's do the same with HI. H2 plus half I2 gives HI. There's a half of that. Half of that gives me that. And this is plus 26 kilojoules per mole. All right, that's what it means. Now, what is it nothing to do with? It's nothing to do with the hydrogens because they're in both equations. So it must be something else. Now, let's have a look. Which statement is the most important in explaining the difference between this and this? Why is 192 and why is 1 plus 26? Chlorine is more electronegative than iodine. That is true, but it's nothing to do with the energetics. Okay? The activation energy for H2Cl2 reaction is much less than that for H2I2 reaction. Is this true or false? B. Anyone want to answer? You can turn on the microphone if you want. What do you think about that? Somebody thinks it's true. Now you're guessing, I can tell from the question mark. Anyone else? Is anyone else there? It's just Moses and Bazad, isn't it? You guys, you're not looking at what's going on. Okay. You're there, Wada. Well done. Wada, what do you think? Is B true or false? False. Oh, Bazadi, that'd be. Oh, Bound is there. Sorry, I thought that was Bazadi. It is false. Why is it false? Are we just guessing it's false? It is false. But why? Why is that false? If you don't IDK, if you don't know. There, well done, Bona. Exactly that. Drawing out exactly, it does help. All right, well done though. But Bona's very, very correct there. All right, now let's think about it. If I have H, let's draw out the two things. There's one, and there's another one. And we're not doing that many questions, are we? But that's good because we have to dig into the hard stuff. H2 plus Cl2. And this one is H2 plus, oh, not Cl2, is it? H2 plus I2. Okay. Now, what do we have to do to H2 and Cl2? We have to break the bonds. Okay, so initially, we're going to have to put energy in. Now, Barney exactly had it. We have two bonds now. Now, it's nothing to do with the hydrogens because they're the same in each of them, aren't they? So basically, the activation energy is going to be about which bond is easier to break, the Cl-Cl bond or the I bond. Okay? And Barney said it exactly. Now, if you've forgotten this, you've just got to kind of remember stuff like this. But if you remember Cl, Cl, and I, which one of these bonds is longer? The Cl, Cl, or the I? Oh, that was going on there. Which one is longer? Obviously, because no one's answering, the I bond is longer. Therefore, which is the weaker bond? The Cl, Cl, or the I? The I bond is weaker, isn't it? Well done. And therefore, which one is going to require less energy to break? The I. Yes? So, look, I know there's there's a long logic sequence here, but if the I is easier to break, it will have a smaller activation energy. Do you follow that reasoning? Because we have to break the I bond, and therefore it will have a smaller activation energy. Now, look at this statement here, B, and look at that. None of you, or very few of you, I think Bonet and Wanda maybe, but none of you really understood that question because you're thinking, how the hell do I know about the activation energy? But the thing is, you have to bring in other things. You have to bring in bond length to realize that it's harder to break a ClCl than it is to break an II. Therefore, the activation energy for the H2Cl2 is going to be bigger than the H2I2. Do you follow that? Sometimes there's like levels and levels. You can't just look at multiple choices and get the answer. I promise you, you can't. All right? It's not like IGCSE when the answer's in front of you. This one takes like levels of understanding just to understand that that's wrong. You can't do these like the night before. You can't. You have to swim in these things. All right, so that's wrong. Well done. We dug it out in the end. The bond energy of HI is smaller than the bond energy of HCl. Okay? Now, what does that mean? It means if the bond energy of HI is smaller than the bond energy of HCl. Okay? Now, what does that mean? First of all, is that true? Is that statement true? I'm not saying is that the answer, but is that true? Is that a true statement? The bond energy of HI is smaller than the bond energy of HCl. Is that a true statement? Anyone want to guess? It is true. Why is it true? Because it's a longer bond, isn't it? Okay. Now, if HCl has a stronger bond, everyone listen to the reasoning. If HCl has a strong bond, which you know it has, when the HI is formed and when the HCl is formed, which one gives out more energy? The formation of HI or the formation of HCl? Anyone. Which one gives out more energy when it is formed? The formation of HI or the formation of HCl? Well done, Moses. Yes, it's the form. Well done, Marang. Oh, Marang, I didn't know you were there. It's the formation of HCl, isn't it? So, and I know this sounds really hard to do, but when you have the individual atoms up here, and you have the HHII, which one is going to go down more? Which one is going to be more exothermic? The HCl or the HI? Which one's going to be more exothermic when these things when they form? Yeah, Moses is the HCl. So which arrow is going to be bigger? This one is going to be bigger than this one. So overall, which one is going to be the more exothermic overall reaction, and which one is going to be the more endothermic overall reaction? Which one is going to be the more exothermic? It's the HCl, I'm telling you there. And that's what we see. So why is it more exothermic? Because of this. The formation of the product is more exothermic. That means it goes down more. Yes? Does that make sense? Yes? Because in the formation of the products, it gives more energy out because the bond is stronger. The HCl bond is stronger, and therefore in its formation, it must give out more energy. And the HI bond is weaker. That means in its formation, it gives out less energy. Does that make sense? Energetics is very, very, very logical, but you do have to know a lot of, as I say here, lots of levels of understanding because it sucks otherwise. All right. I hope I'm not scaring you off, anyone. It's a lovely subject, and maybe we should do another one on these, maybe on longer questions, on paper 2 questions or whatever. All right. Anyway, there you go. So the answer is C there. The reason it's more exothermic is because of this fact. Okay, and it goes down more, so that's the answer. Now, the bond energy of I2 is smaller. It is smaller than the bond energy of ClCl. But why doesn't that really matter? It doesn't matter because this is the endothermic part. We're breaking these, and we want to know about the exothermic part. Lovely indeed. Thanks, Bazali. I like it anyway. All right, there you go. Well done. Let's do another one. All right. I didn't realize this was going to be so involved, to be honest with you. I thought we just rattle through these, but it's good. This is better than I thought, to be honest with you. I like doing, I like digging into the answers, as I'm sure you all do. This one is quite straightforward, though. Ta-da! All right. Now, well, I hope you can do these. I find these quite straightforward. All right, so I use what are called Hess's triangles for these. Okay, so I do this: 3 magnesiums react with 1 potassium chlorate, gives me 3 magnesium oxides and a KCl. All right, this is and they give us formation data. All right, so down at the bottom here, I'm going to draw the elements. I'm not even going to bother. It's multiple choice. Who cares? Okay, so I'm going to say the elements are down here. Who cares what they are? Okay, so I've got to form some magnesium from the elements. I've got to form some potassium chlorate from the elements. I've got to form some magnesium oxide from the elements, and I've got to form some potassium chloride from the elements. But I want the enthalpy of this reaction. So this is the one I want, delta HR. I want delta HR. What is delta HR? Well, I'm going to call the elements on this side, I'm going to call this delta H1, and the other side I'm going to call it delta H2. Okay? Now, according to Hess's law, all right, going from here to here must be the same as going from here to here and then up to here. Okay? That's a conservation of energy thing. That's Hess's law. All right? So let's get rid of this. So according to Hess's law, then, delta HR, the top one, I go from here to here, must be the same as going this bottom route. The bottom route is minus delta H1, because I'm going against the arrows, aren't I? Plus delta H2. And this is the way we write that. Now, what is delta H2? Delta H2 is the formation of 3 magnesium oxides. Go up here. I need 3 magnesium oxides. So it's positive, isn't it? Delta H2 is positive, yeah? So this must be wrong. A must be wrong because it's got minus 3, yes? This must be wrong because there's not 3 of them. This one's wrong because there's not 3 of them. So the answer must be C. Okay, I'm going to continue anyway to make sure I get the other terms in C. So I've done that, okay, plus, I'm going to put this in square brackets, plus the formation of KCl. KCl is minus 437, so minus 437. All of this is delta H2 minus delta H1. Now, the formation of magnesium from magnesium is 0 because it's an element. So now I have to form potassium chlorate, which is minus 391. And this term is delta H1. Do we all understand that? And obviously the answer is C. Anyone there? I'm going to have a bit of chamomile tea. Are we good there? Does that make sense? If it's not good, I'll do it again. Well done. All right. You see, it is lovely, isn't it? So there you go. So the answer is C. You'll be fine, I'm sure, honestly. The multiple choices, though, we weren't great, were we, in our exam? That doesn't matter. We'll get there. All right, another one. Yeah. All right, where are we? Let's make this big. And let's make this small. Okay, there we go. All right, the standard enthalpy change in formation of that and that, on that and that. What's the enthalpy change for this reaction? Well, it's a very similar question. All right. Fe plus 2Al gives 3 Fe's plus Al2O3. I'm going to start down here. I'm going to have 3 iron atoms plus 1.5 oxygens plus 2 aluminiums. I've bothered writing the elements there. Normally I wouldn't bother, but I thought, well, what the hell? Going up here, well, aluminium to aluminium is nothing, so I can ignore that one. All right, and so basically this one I'm making iron oxide on that, iron to oxide. The other side, well, iron to iron, I can ignore that one because that's 0. So all I'm doing on this side is making aluminium oxide. This is the one I want, delta HR. I'm going to call this delta H1 and delta H2. All right. Now, delta HR is equal to, I'm going from here to here is delta HR, and I could go all the way around that way. So delta HR is minus delta H1 plus delta H2. What's delta H2? Delta H2 is the aluminium oxide, iron and aluminium oxide, that and that. So the last one must be that one. So it's delta H2 is minus 1676 minus whatever delta H1 is. Delta H1, I think, is that minus 266. And there you go. So I'm adding 266 to that. And it's going to be a 0 at the other way that I want it is. All right. Does anyone know the answer? Oh, I'll do it. Yeah. So I have 1676 and 266. I get 1410. Oh, I've done something wrong. Have I done something wrong? Oh, hold on. 16. Let me do it again. 266 minus 1676. Yeah, minus 1410. What have I done wrong? Anyone? Have I got them the wrong way round? Oh, can anyone see? I'm going to leave this to you. All right. I know it's an easy question, but I've got it wrong. Oh, well done. I didn't multiply by 3. But do you get that, though? Well done. I didn't see that, did I? I was horrible. So I've got to do, which one have I got? This one is 3, isn't it? Is that right, Basali? Have I done it right now? So if you do it now, we're good. So are we all happy with that? Okay, well done. I don't know. Oh, let me do the answer. Oh, so it's 266 times 3, 798, 798, 1676 minus 798 is 878. And it's going to be B. All right, there you go. If you want to, if I get some things wrong, and I will get things wrong, don't worry about it. But there you go. All right, well done. The next one, gosh, time flies. It's already 10:02. Right, we'll only manage to do a few more, I'm afraid. That one, oh, this one looks nice. Oh, we've seen a similar one already to this. Diamond and graphite again. Let's make this bigger. Make that smaller. Okay, there you go. Diamond to graphite. Well, we knew graphite to diamond is +3, so diamond to graphite must be -3. There you go. Piece of cake. Why doesn't this occur spontaneously? Well, first of all, do we understand what spontaneously means? Something that we kind of assume you know, but I don't know. Spontaneously means it will happen without you doing anything. Okay? Now, let's have a look. Why doesn't, let's draw it on a diagram again. Okay, if I have diamond here, there's diamond. Graphite is here. Why doesn't diamond just change into graphite? Because it's more stable. Graphite is more stable. It goes down an energy well, as they say in physics. Okay, so graphite is more stable than diamond. So why doesn't diamond? If you imagine it like this, there you go. If you have a ball on a hill, this is at the top of the hill. This is diamond. At the bottom of the hill is graphite because it's less energy. So the ball should roll down the hill, shouldn't it? So in other words, diamond should spontaneously, that means on its own, without us doing anything, should make graphite. Why doesn't a diamond ring turn into graphite? Does anyone know? According to the energetics, it should, because graphite is more stable. So why doesn't diamond turn into graphite? Anyone know? Oh, no. Tetrahedral configuration is always more stable than a planar one. Where the hell did you get that one from? No, it's horrible. Why doesn't it do it? Which one do you think prevents the reaction from happening? Why doesn't diamond turn into graphite? No? You know what? It's for a country that digs diamonds out, everyone, we should really know this one. Imagine you give your husband or your wife a diamond ring, all right? And oh, I love you. There's a diamond ring, all right? And they wake up the next day and it's turned into graphite. Do you think that would be good for the economy of Botswana? We should really know why it doesn't. All of us should. Seriously. Okay. Anyone want to guess? What have we got to do? What does diamond have to do to change into graphite? It is C, Bazali. Well done. All right, let me draw a diagram again. All right. Now look, there's diamonds and there's graphite. What must you do to diamonds first before it can become graphite? It doesn't just going to change. Oh, there it goes. It's changing. What must the diamond do first? No one's answering, so I'll answer it. You've got to break the diamond up in graphite into atoms of diamond. You've got to atomize it first. Is it easy to atomize diamond, do you think? Anyone can answer. Basardis, you've got the right answer in the end, so you can answer this one. Is it easy to atomize the diamond? Of course it isn't. In other words, it takes an enormous amount of energy. Look at this. This is very, very, very big. So, what do we call that? That's the energy required to break up diamond into its into its carbon atoms, isn't it? So, what would you say? Oh, that's going to take a lot of energy. But what would you call it in terms of this graph? In terms of this question, it has a very high. Besides, don't ask questions yet, dear, because it has a very high what? Very, very high activation energy. Yes? So Basadi's come up. So before I read Basadi's one, are we all good? Diamond has a huge activation energy. Okay? Now, but then if it's C, won't that mean the high energy needed for atomization? No, why would it be that, dear? Does only things with a tetrahedral structure have a high atomization? What about methane? Basadi, I'm looking at you. What about methane? Can we burn methane? Is it relatively? It has a very high energy because the carbon-carbon bonds are covalent, aren't they? They're very, very strong. Carbon-hydrogen bonds are a lot weaker, so we can easily convert methane into carbon dioxide and water. Because if you look it up, carbon is a lot stronger than carbon-hydrogen bonds. Yes. All right. Now, but they're both tetrahedral, so the configuration doesn't really have anything to do with their bond strength. Yeah, that's what you've got to do in these questions. You've got to dig deep. Now, let's have a look at the last one. Oh, God, that looks horrible. Shall we do a hard one? Let's have a look there. Let's have a look at this one. I don't know. It looked horrible. I hope it's not as bad as it looks. Oh, look at that one. It's one of these 1, 2, 3s. One explanation of the explosion at the Chernobyl nuclear plant in 1986 is that the graphite reactor overheated and reacted with the cooling water according to the following equation. Wow, look at that. So, carbon reacted with water and you got hydrogen gas and carbon monoxide. And then they'd react with oxygen and a huge explosion would happen. All right. What are the possible reasons why the forward reaction is more likely at higher temperatures? So let's draw the picture to see if we can get any insights. There's the picture. This is energy. Okay, so we have, where are we here? Carbon plus water, and apparently hydrogen and carbon monoxide. So this gap here, the energy gap, is 131. And obviously, overall, it's an endothermic reaction. All right. So, what are the possible reasons why the Ford reaction is more likely to occur at high temperatures? Okay. Well, without even looking at the question, can anyone tell me what's likely to be a reason? Why do reactions only happen at high temperatures? What does that mean? If it doesn't happen at a low temperature and only happens at a high temperature, what does that tell you about the reaction? Does anyone want to guess? If reactions only happen at a high temperature, it must tell you something about the activation energy. Because if the temperature must be high, the activation energy must be high. Okay? Because otherwise you wouldn't need a high temperature. You need a high temperature to break things apart. All right. So let's have. Oh God, what the hell's that? Right. Let's have a look at this then. So, what are the possible reasons why a Ford reaction is more likely to occur at high temperatures? Hydrogen and carbon monoxide do not react at high temperature. Well, that's rubbish. Okay. Why? Why? Why that? Why? That's rubbish, isn't it? We all know hydrogen does react at high temperatures because it easily burns, doesn't it? You know that from the Haber process, even. All right. So even understanding that one is an understanding Haber process. At low temperature, the position of the equilibrium lies too far to the left. Well, at low temperatures, yeah, you know that Le Chatelier at low temperatures, the equilibrium will lie on this side, won't it? So this is true, and the activation energy is high. Well, yes, it is going to be very high, because that's why you need a high temperature to initiate the reaction. And also, where are we here? All right, where are we? There. And you also you're breaking up carbon. Carbon has very, very strong bonds between it. As you all know, in group whatever it is, in period two, it has the highest melting point, doesn't it? The um, the carbon carbon bonds are very strong. So that answer is two and three are correct. So in the old days, we'd say the answer is C. All right. Now, I think we'll sign off on that. An hour is long enough for anyone. Now, listen, guys, I've noticed that your understanding of this particular topic isn't wonderful. All right. Um, yes, Basali, hold on, dear. But I think you should all hit the books on this topic and make sure you understand it. I have no problem helping, obviously, and maybe paper two questions. Paper one questions are a bit brutal. All right. Maybe I should have done paper two. I think paper two questions are easier. All right. So maybe we should do another one of these because I'm not really convinced um, that you have a good understanding of this. All right. So I think we should go in a bit more gently into paper two. All right. Paper one are hard. Okay. All right, Basali, what's the question, dear? Are you going to say it or are you going to type it? It's up to you. Just don't shout when you do it because you scare me. Oh, let me turn off the video.